So let's first of all quickly summarize what we have learned about the photoelectric effect last lesson. So three findings of the photoelectric effect which could not be explained by the wave theory of light. First, the existence of the threshold frequency. According to, if we consider light as a wave, there should be no threshold frequency. Electrons should be getting out of the metal for any frequency of the light. It should depend on intensity, but not on frequency. So that's one thing that cannot be explained by the wave theory. Second thing that cannot be explained by the wave theory is the absence of time delay. For dim light. So, according to wave theory, if light is very dim, so not enough energy, electron might accumulate, come in light, accumulate, and eventually get out. So photoelectric effect will start, but with a delay in time. But it's not happening. The electrons either get immediately or never. And the third thing is that the stopping voltage depends on frequency of the light, not intensity. So, doesn't matter how we change the intensity of light, it's not affecting the voltage that needed to stop electrons from getting through. But if you change frequency, it affects stopping voltage, change stopping voltage. So those three things cannot be explained with the wave theory of light. And as we already discussed, Einstein's come with the explanation. And the equation of the photoelectric effect is effectively the law of the conservation of energy. And by the way, I was right in mind because I was thinking about next step, what I will do now, I arrange this formula, and W will become with a minus. So it has to be with a plus. So what is this? Is the law of the conservation of energy. This is the energy of the photon, particle of the light, which some used for electron to get out. What's left will be kinetic energy. And just want to underline a couple things, that it's not just kinetic, it's maximum kinetic energy of electrons, and this is called walk function. And walk function, again reminding, it's a minimum energy required for electrons to get out. Minimum energy. So, if some electron needed less energy, it will have more kinetic energy. It will have kinetic energy maximum. Let's rearrange this equation. So, kinetic energy of the electrons, or photoelectrons they also often called, will have hf minus walk function. Let's sketch the graph of this equation with the kinetic energy being on the y-axis and frequency being on this axis. this, so we have, this is our y. Effectively we have y equal mx plus c. We have equation of the straight line, where y is kinetic energy and x is a frequency. So that what will be the graph, will be the straight line, with this being threshold frequency, the minimum frequency at which electrons can get out. At this point we will have that all energy of the photon equals work function. Electrons just get out with a zero kinetic energy. What will be the gradient of this line? Planck's constant. Yes. Gradient of this line is a Planck's constant. H is a gradient. And this will be negative work function. Important thing, work function is a positive number, it's energy required. So this will be not W, it's negative, minus W. It's minus W. If, let's say, we change metal with a higher, with a bigger work function, so require more energy for electrons to get out, how the graph will change? It will be parallel. It will be parallel, but it's required bigger work function. But gradient is the same because it's Planck's constant. So that's how the graph will change if we change the metal. Take the metal with a higher work function. So for electrons it's harder to get out. Make sense? Now, when we apply stopping voltage, so we have electrons coming from here, light falling on this plate, electrons flying out, but we apply minus here, plus here. An electron stops and pushes back. What happens to kinetic energy? Electrons comes out with the kinetic energy, but where it stops momentarily, its kinetic energy is zero. What happens with that kinetic energy?
Potential?
Electric potential. It turns into the electric potential energy. So let's recall. Actually, should not erase the graph. So, what the formula for electric potential energy? Who can recall from the previous semester? Charge times voltage. So we will have that when electron stops, due to electric field, we will have that kinetic energy max equal Q, charge of electron. Reminding the charge of electron, we're talking about electrons, equal 1.6 times 10 negative 19 coulombs. So all kinetic energy turns into the electric potential energy. So we can rewrite Einstein's formula for photoelectric effect as QV equal HF minus W. Electrical potential, and where this is stopping voltage. This is a stopping voltage. Voltage which stops electrons. Even fastest electrons from reaching the anode. Because negative electrode called cathode, positive anode. From where electrons coming called cathode, and the other anode. So this is pretty much, we just replace kinetic energy maximum by QV. Let's, yes.
Is the stopping
voltage, like the voltage for it to not go to the negative plate?
That the voltage, when we apply minus here plus here, because electron has negative charge, an electric field will push him back.
Okay.
To push it back.
But can it not be like a range?
No, it's when it just stop. Of course, if you apply higher voltage, of course it will stop. That you're finding what the minimum voltage will stop.
Right. So just before it gets to the negative plate.
Yeah, which stop them before getting to the negative plate. Yes. Now let's divide this. In this equation, we have energy, everything in joules. Everything in joules, and so Planck's constant in joules. 6.63 times 10 negative 34 joules second. Now let's divide both sides by charge of electron. We'll get stopping voltage equal HF minus W, but why I have not changed anything here. Make it in other unit. If we divide this number by 1.6 times 10 negative 19, we will get Planck's constant in electron volts, 4.14 times 10 negative 15 electron volt seconds. If we divide work function by 1 in joules by 1.6 times 10 negative 19, we will get this this was in joules, that was joules. Now it's all in electron volts. Electron volts. So we change the unit of measuring of energy from joules to electron volt by dividing by the charge of electron. So we have, even effectively here we have energy, but the energy of the electron when it stopped, Q times V stopping in electron volts, will be exactly equal to the number of volts. So that if you take this in electron volts, this in electron volts, we get this, what is equal the stopping voltage. We'll get number of the stopping voltage. And graph will be exactly the same of the stopping voltage against the frequency, same as it was. Stopping voltage, and it depends on the frequency, against frequency. By the way, why when we were draw previous graph, kinetic energy maximum against frequency, it came only up to here, and then I draw dashed line. Why I didn't continue the solid line and put a dashed line? Yes?
Does it not have any kinetic energy before it leaves the middle?
Because negative, it will become negative. Negative kinetic energy doesn't make any sense. It doesn't exist. So effectively, it's here has zero kinetic energy, just get out, and then just continue line to find the work function. Make sense? So here, all perfectly from the when we consider light as a beam of particles, photons, everything perfectly makes the experiment. We have threshold frequency, minimum frequency, at which electrons can get out, which equal that frequency. We have H times F. Threshold equals work function.
So is it the same
Intensity
thing?
does not.
Is it the same thing there? It's zero. No, for the stoppage one, for the
Stopping voltage here, exactly the same thing.
Like in the center.
But it will be again, but we have, remember we have it's in different units.
No, but I'm saying it's zero below the, yeah.
We have It's threshold frequency. So it will be same frequency.
No, I meant below the x-axis, it's effectively zero.
It's voltage, but it doesn't exist. There is no opposite stopping voltage. And we have that stopping voltage depends on the frequency. And there is nowhere intensity involved, anywhere here. So it's not affecting energy of the electron. What changed if you look from consider light as a beam of the particles, of photons? When we change intensity, what we actually change? Do we change energy of, we have monochromatic light with a one frequency, and we increase intensity. Do we change energy of each individual photon? We change the number of the photons. If we increase intensity of the light, we just have more photons coming. But each of them have the same energy. And it doesn't matter how many photons come in, each of them still have the same energy. And if that energy is not enough to overcome Bohr function, doesn't matter. It's 100 photons, or 1,000, or millions of photons. Still, none of them have enough energy to kick electron out. Yes?
If light acts as a particle, then how can it have a frequency?
That the light has both properties. Does it have wave properties? Yes. Young double-slit experiment, another experiment showing that light can diffract, can be interference of the light, which is a wave property. So light has a dual nature. It has wave properties and particle properties.
But the calculations
involve frequency. Involve frequency, yes. Involve frequency. But consider the A is a particle. If you make with more frequency, just photon will be more energetic, has more energy. And so, as one, I forgot who is, one physicist said that light on Monday, Wednesday, Friday, light behave as a wave. On Tuesday, Thursday, Saturday, it behaves as a particle. What it does on Sunday, nobody knows. And I will say the best way to think about it, I'm not saying that exactly what it is, but that the light, when light is traveling, propagating, it's behaved more as a wave. When it is emitted and or absorbed, it behaves more as a particle. It's not like exactly 100% correct, but in general, give you a good idea when to consider which properties are more dominant. By the way, later on in this course, we'll learn that particles have wave properties. Electrons can behave as a wave. By the way, each of us have wave properties, but we'll discuss it later on. And we just will find out that the wave property, wavelengths, let's say, associated with a like person like me will be like wavelengths will be 10 and negative, like 30 something, which is not detectable. Now, one more thing. If you sketch the graph of the current, if you measure the current that's getting through against voltage. So we have current against voltage. This is positive voltage, so we have the plate on which light falling. We have minus here, plus here. That is at this part. At this, we have plus here, minus here. Now, and the graph, I'm drawing you like not that exact how the graph looks like, because of the ideal representation of the graph, simplified. That's how the graph looks like. Of course, it's not like those straight. In reality, it will be a little bit like this, but for understanding, for our purposes, we consider it like this. Questions? And this is the stopping voltage, where current becomes zero. All electrons stop. Yes?
What are the two different things on the top?
This is the two plates.
Yeah.
On this plate, the light falls on this plate. But that we applied here minus here to the plate from where electrons come in. So here we have voltage applied, negative on the plate which is illuminated by the light, plus here. So in this case, will be electron stopped. Will be electrons coming out from this plate, because light falls on this. Will this arrangement stop electrons? No, because they will be attracted there. Nothing pushes them back. Here, when electrons comes out, electric field pushes back and can stop it. Now, why we have this horizontal? Why we increase in voltage, we're not getting more current? Any ideas? What getting electrons out? Is a voltage getting electrons out or light? Light. If we increase voltage, will we get more electrons out? No. It all depends on the light. So when we increase voltage, we don't have more electrons. Because electrons come in as a result of absorption of the photons. Make sense? And here, as soon as we start apply negative voltage, here we stop some electrons, more voltage, more electrons, more, and here we stop the fastest electron, the current becomes zero. This is current voltage characteristic. Now, if we will increase now intensity, we keep frequency same, F same, intensity increased. What will change with the graph? Will stopping voltage change? If we increase intensity with the same frequency?
Yes.
No, because photons have the same energy. Increase intensity, what we changed? More photons. So we will have same stopping voltage, but we will have more current. Because we have more photons coming through. But to stop them, we have more electrons coming out because more photons came in. But energy of each individual photon the same, so the maximum kinetic energy stay the same. What will change if now we will have intensity same, but we increase frequency, same as in the first case. We have the same intensity, but we increase frequency. What will happen?
Same
What happens with the stopping voltage?
increases.
Yeah, we need more voltage now to stop the electron. It has more frequency, so photon which come in has more energy. So electron which come in will have more energy. So graph looks like this. More frequency, higher frequency, we will require more voltage to stop electrons. Okay, that's all for today. Please like, subscribe and donate to help fight terrorist countries and organizations like Russia and Hamas, support Ukraine and Israel.